Awesome. So now we're going to hear about dust implementation in common envelope simulations. Yeah. Yes, yes.
Okay, give me a second. Yeah. Good. Can you hear me? Yeah. You don't know? Ah. Oh, okay. Oh, yeah, yeah. You can hear me. Uh, well, hello everyone. My name is Miguel Gonzalez. I'm going to present about those implementation in common envelope simulations. And this actually is pretty much like the work I've been doing in the whole PhD. So I want to try to be do it really quick here. So I work with Ursula and Mark at Macquarie University. And this collaboration is with Leonel Cis, Luis Carlos Bermúdez Bustamante, Daniel Price, and also I presented previous work with that I collaborate with Mike Lau, Ryosuke Hirai, and Mansi Kansiwal. Yep. So I'm just going to try to be really brief here because everyone knows by this point what is a common envelope. Basically, it's just an evolutionary phase that happens in binaries. First, you have the primary component starts to expand. Then you have the Rochelot overflow. And after that, you have the common envelope, right? That's after the trigger of unstable mass transfer. Well, in my case, I study low mass binaries, which means that one of the main goals here is try to understand how can you create these beautiful observations, not create observations, but having this planetary nebula. So we know that after discarding a lot of possible explanation, that the only way to form a symmetric planetary nebula or APN, it's by having a post-common envelope system, right? So that's one of them, our main interests. Until very recently, until I don't know, 2018 or so, most of the works in common envelope simulations were done using RGB stars. However, ever since like 4 years ago, more people have been start working on AGB donor stars implemented in common envelopes. Okay, so RGB is here, just to give a quick recap. This is just basically just how the radius of a two solar mass star is evolving over time. And you will notice something interesting. This is basically the early AGB phase, and this is the thermally pulsating AGB phase. So if you want to know, if you want to see if a star will, if a binary will trigger an unstable mass transfer, you would like to do it in a place that is more likely to happen. In this case, it's a really good candidate to do it during the thermally pulsating AGB phase. What is the problem with this? Well, in this phase, in this H diagram, I'm pretty much showing there that it's basically right at the end of the life of the star. You have that it's really unstable, and these thermal pulses basically is just are occurring because of the helium flashes that are occurring in deeper layers of the star, and this tends to have to be have that time scale of a couple of centuries, which means that you pretty much have to you have to work with a star that is really unstable because it's really expanding. Here, I basically have the thermal pulse is happening in the range between 260 solar radii, and it goes a little bit over 300 in a span of a few, almost 2 centuries, right? So it's a really rapid expansion. And the problem for this is that you really have to expand it and make it work. Now, the question is, can we work, can we take one of these stars, assuming that it reaches the Rochelot size at the beginning of the thermal pulse, and if this does, is it possible to make to trigger the mass transfer to begin the common envelope interaction? Spoiler alert, well, it can be done in simulations, right? For this, we use MESA, which everyone here is 1D code to model and evolve 2 solar mass and later a 4 solar mass star. And then we implement a Phantom to make the binary system. Right. So just a quick recap about Mike I was mentioning before. We evolved the most important 2 models we did was one with ideal gas and another one with using the MESA equation of state. to account for recombination energy, right? So in the old technique, what you have to do was just adding a damping force for the velocity of the particles, and it worked pretty well for ideal gas, right? So here, yeah, so here you can see, if you remember on Mike's talk, there were like these pizza topping, pizza slices, right? You are probably were see it at the beginning. And this happens, but they tend to stabilize fairly quick if you let it go enough after the damping. The problem is that when you try to implement this particular model that is expanding, remember, this is a really unstable model to begin with because it's a rapid expansion star, using recombination energy, right? You cannot use the same method. So here we use relaxomatic that help a lot. Actually, before this, it was actually exploding the star. It took me a few months to figure it out. And even though it's a little bit more fluffy, that makes sense because you have more thermal energy in the gas, right? So just, and actually I took the first months of my PhD working on making sure that I have a fairly stable star to work with. Here I'm doing a comparison for different models using different equation states and resolutions. The one that actually matters is basically the red and the orange one are ideal gas and Mesa equation state. You see that the ideal one actually is fairly stable. The rate, the expansion is pretty much stable, just pulsating a little bit. Doesn't have anything to do with the thermal pulsating, just actually the pulsation of the numerical instability. And the dotted line is basically the evolution, the radial evolution of the original Mesa profile in 1D. So pretty much we want to compare how fair the expansion of these models were against each other. And we realized that the one with ideal was actually expanding slower than the Mesa model in 1D. But the one using the Mesa equation state, the red one, actually was expanding really rough at the beginning, really, really fast. But after that, it has a stability period. So we said, okay, good enough, right? Just to be sure, just a few comparison with the density profile of all these methods. Again, just the first one and the last one are the second one and fourth one are the ones important. After mapping, you notice that there's a lot of noise in these methods. Is because, again, like Mike was mentioned before, you have the rate, instead of using the geometric lattice patterns, you use a random one. That's why it looks a little bit noisy. But after relaxation, well, the mapping with the relaxomatic, you have a fairly stable and a pretty good model to use in the binary, right? Okay, yeah, whatever. Nobody cares about that, right? So this is one of the models. I use the ideal one here because, to be honest, it's the prettiest one. The Mesa one just makes a radial expansion. And I'm just here just showing like a cool matrix effect doing the spinning here. After 15 years, you pretty much finish with the Rush-Low overflow. And after 20 years, you pretty much finish with the whole interaction, right? Yeah. And this is good because this model was the one that took the longest, which means that if you remember previous times of thermal pulse, this is one order of magnitude less in time scale compared to those, which means that at least its simulation is possible, right? Right. Now, how about the results? Well, we have, I'm going to focus here just in separation and bound mass. This is for all the models. We notice that when you include, of course, when you include the Mesa equation state for the recombination, you unbound more material, right? This is just the amount of mass bound. So you almost unbound everything, right? Then you have a certain, you have the first part, which is the Rush-Low overflow, which is highly dependent on the resolution and the stability of the stars. The plunging, which is completely dynamical, it's pretty much the same thing for everything, almost there, except for the fact that it's a little bit smoother for the Mesa equation state. And then you have this additional unbounding that happens right at the end. I'm going to talk about that later, but I want you to notice it, that you have a second, more aggressive unbounding here, right? So for these results, we found that the separation is larger for lower, yeah, for higher resolution, you have a higher separation. Sorry, no, for high resolution, you have a lower final separation, which is different from what we found in previous work done by Ricard in 2019. The difference being that they made it with a RGB star. We use a RGB star. So it's really interesting, the fact that you have the opposite behavior in terms of comparison between resolution when you are using RGB star or AGB star. And of course, we have more inbounding in using more energy budget in the gas. Right. So another comparison that we did with Ricard, in 2019 and 2020 was the opacity, right? So the problem here is that you have the contour plots. I don't know if you can see the black contour here is for temperature of 5,000 Kelvin, right? This is for Ricard. In our case, we did it for 5,000 Kelvin, the inner one, and the outer one is for 1,500 Kelvin, which is roughly the one at which you will start having dust condensation, right? So you have these two regions in which you have a high opacity. The problem is this: the outer region, everything is being mapped with the MESA kappa tables. The problem is that for real low temperatures, you cannot trust too much in the extrapolation made by the tables because it highly depends on which density are you having the values. So we said, okay, what next about this? Well, we can try to work with dust, right? Makes sense. And for this, the second part of my project has been working on using the Bowen prescription, which is a fairly simple first approximation for assuming the dust formation and the influence in the dust-driven winds, in which you basically have it, you basically apply a kappa that is a function of temperature, is that equation, and you add that, you take that kappa and assume, and you add this last term for the dust-driven wind, right? So this allows you to have extra term that will pretty much push forward the gas when you have a high enough kappa, right? Right. So we did the same thing. We apply it in the original models, and also we implemented it for solar mass models too, because you have the CO ratio inversion that happens between these two ranges, between two solar mass and four solar mass, and they tend to happen also in the thermal pulsating phase. Yeah, so that was the effect. Of course, we have to put that Roche overflow again. So the initial distance is fairly different, right? And well, I don't want to make it long story short. We make it. This analysis is for the two solar mass first. So what we did here was, since you have to use certain parameters for Bowen, which is the maximum kappa that you're gonna use, that you would allow the dust to have, the delta D, which is just the condensation range of the temperature, and finally the condensation temperature that we set at 2,000 Kelvin. And after that, we just start model it. In our case, we use two different values of kappa max, which is 5 and 15 grams per centimeter square. And we noticed that when you have a higher kappa, you will have a higher effect in the separation and bound. For instance, the separation is larger for higher kappa, and the unbound is larger, which means that you are taking less energy for the orbital budget to unbound the system. And yeah, you still have this huge slope that I'm gonna talk about in a moment. And for MESA, you pretty much are increasing the already big unbounding rate that you have. For 15, between no dust and 5 dust is pretty much the same thing. For 15, you have a quite large difference. Yeah, and for the 4 solar mass, interestingly, we didn't find too much difference in the separation. We did found that there's the Roche overflow is time scale, it's shorter when you include dust, which makes sense because the gas that it's at the beginning is in the surface is a little bit cool, which means it will have the highest acceleration due to the dust, which means that it will reach the companion, which means it will trigger the mass instability, the mass transfer instability sooner, right? And in 4 solar mass, we have this interesting dip in the bound mass, which means basically you pretty much unbound the whole system right at the beginning. However, the whole interaction is dynamically driven because for the 4 solar mass star, we use the same mass of companion, which gives you a lower mass ratio, which gives you a easier, a less stable system, which means you will trigger the common envelope sooner. Right now, just another movie. This is for the dust. So here I'm trying to show you the main phases. You have first the rush low overflow, and then after, in this case, 7.6 years for the ideal with 15 of kappa, you have the spiral really fast, really dynamical driven, and after that you have the post-common envelope system, and after that you have this resolution we call it artificial unbound, but it's resolution dependent unbound, right? So what is happening is that the inner part of the star, of the primary, it's depleted of gas, which means you don't have enough resolution. But also you have this, since you have this modification of the core particles, this modification of the gravitational potential implies that you will have a negative pressure gradient for the particles, which means that it will be ejected when you have low enough of them, because you don't have enough gas to account for the gravitational interaction, which means that the pressure is not enough and they will just pretty much be ejected. This is actually a problem that it can be solved when you increase the resolution, and there have been some proposals to fix it, but other than that, as long as you account for that, it's fine to just consider everything before that to be suitable. Also, you will notice that this tends to happen when you have a really low orbital distance, because by this point, basically you have an empty region in the central part, or empty enough to trigger this effect. Anyway, so how about the opacity now? Well, we have two different, the bow one with these two values. And this one is a work that is being done by Bermudez Bustamante, it's in prep, and our own work using Bowen. You will notice that the distribution of the particles, well, the distribution of the outer layers of opacity is pretty much the same thing, but you will have this gap, this empty gap. The reason we don't have that gap is because of the function of kappa itself, which is what is it called? Synode, no, synode function, which is just like an S. The problem is that that function is pretty much like an on-off switch of the opacity, and that doesn't leave too much room to have any phase transition regions of the dose of the dose-driven wind. You pretty much go from no having any opacity to the dust, and to have the highest one. So that's one of the difference compared to nucleation. The other difference is that you pretty much are depending a lot in the maximum value of kappa. However, the good thing about Bowen is that it tends to be a lot more efficient to run the simulation, which means it's faster, and it's a good checkup as a first approximation to confirm your results with nucleation. Right now, how about the acceleration itself? So in the top panels, we have the density of the two solar mass models, and in the bottom one,
left, sorry.
Oh, yeah, that was fast. In the bottom one, you basically have the acceleration of them. So we pretty much predict that you will have around 5 and 10 kilometers per second additional for the cooler particles of gas that will trigger the expansion. For simulations with recombination, you don't see that effect too much, but for ideal, you see it. The winds are particularly strong during the rush low overflow phase. That's why you have the faster interaction. And just for conclusions, you have that the dose-driven winds unbounds more gas in all the simulations at the cost of having a larger separation values. The winds are particularly strong during the rush low overflow phase and during the post-common envelope system. This is good because that they will shape the APN, but also it increases the effect of the resolution, on the resolution dependent unbound. And just basically that is not being affected much for the high mass simulations, and nucleation will be a necessary complement for this analysis. Okay, thanks everyone.
Thanks, Miguel, for a great talk. Does anyone have any questions?
Yeah.
I'm sorry, I'm having a mental blank. Sorry, I forgot my question.
Maybe a bit annoying question, but in the beginning you said that you think all these asymmetric planetary nebula are there because of common envelope. So you think they are really all caused by common envelope, not by like larger separation binaries. You think that's impossible, that you get these very asymmetric planetary nebula without having common envelope?
The problem is that you will have, I mean, for it's really hard to explain the asymmetric planetary nebula with just one star.
Maybe like triples and quadruples can make these.
Ah, well, yeah, of course. But because if you notice, all of these have they can have poles. Sometimes they just have one jet, and whether it's understandable that I mean, obviously with magnetic fields, but that's like the question everywhere, right? Like, oh, what about magnetic field? Well, yes, but the issue is all of these are vastly different, and then you have some that they are not asymmetrical; they are fairly regular. So why is that the magnetic fields are not affecting those, but these two?
Yeah, it's a complex problem.
Yeah. So the best so far the most plausible explanation, and many would argue that is pretty much the best one, or the most likely to be, or something like that, is that one. Now I can change this if someone is scared of it. I'll leave it scared of it ever since I've been, yeah. I've been dreaming about that thing, by the way.
Thanks, I remembered my question, sorry. You showed us, well, at least one of the animations, you had a few solar mass star, and then the companion was quite small. Have you also run like other?
The companion is always 0.6 solar mass. It looks small because it's a point mass particle.
Yeah, no, but I mean, 0.6 solar masses is small for a star. Have you?
Well, yeah.
Tried
Yeah.
other,
Increasing it. Actually, I have a project I've been working about changing changing the mass ratio with different combinations. It's in progress. And I found that, but this is not with dust. I found that contrary to what one would believe, apparently there's a maximum on the mass ratio between 0.6 and 0.8 that you will unbound more gas just by changing the companion alone. But it's not like it's not consistently increasing. It's just in around that maximum.
So if you have a more massive companion, you don't have like the common envelope phase.
No, you have it, but you have more mounting. No, if you don't want, or you want to delay the common envelope, you have to make a Q equals to 1, for instance. That way you will have a more stable binary, and that will, I don't know if we'll completely stop the common envelope or just avoid completely the mass transfer instability.
Thanks.